everyone, this is the last part of 1.1. Lots of stuff packed into 1.1 to get us started. This is asking you to sketch, given the graph of a function, in this case we're given the graph of f prime, we want to sketch its derivative, f double prime, and also its antiderivative. So there's a calc 1 part to this, and there's a calc 2 part to this. Okay, so first function, I've deliberately not given you actual scale, no x and y tick marks, because I just want you to focus on basic shape. So with this one, when we go from f prime to f double prime, that's taking the derivative, which means the slopes become our y's. So if I'm looking at the graph that I'm starting with, this linear function, I can see that it always has the same slope, and that slope is always positive. So constant positive slope becomes constant positive y value, which looks like this. Basically, no matter what x coordinate you pick, you're always going to get the exact same slope, which means your derivative will always have the same y value. And it's really important not to be thrown off by the fact that I'm calling it f double prime. People will think that means I should look at the concavity of this middle graph. What's really key is how many steps apart are you. So if you're one step apart, you've gone from f prime to f double prime, that's just a first derivative, which means it is concavity. Whether you're calling it f double prime or not, it's only the first derivative of f prime. Okay, so when we go the other direction, we have to reverse our thinking, which is always the trickiest. So we want to say that if we're looking at the derivative of function f, that the y values of the derivative are the slopes of the function. So this becomes a little more interesting because my y values change. Right here in the middle, my y value is 0. To the left, it's negative, gets more and more negative as I head left, and it gets positive, and then more and more positive as I head right. So I need to draw a graph that has negative slopes, and they start off really big, negative, and then they start getting less negative, and then right where the x-intercept was here, like this point right here, becomes a flat spot. Zero slope means you have a horizontal tangent, which makes a little flat spot on your graph. And then our slopes switch to slightly positive, and then just get more and more and more positive from there. And we do have a little bit of extra knowledge, right? We know that generally the derivatives of quadratics are linear, not just general. We know that's true. That's not just usually, that's always. So we can expect that if the derivative is a line, that the antiderivative will be a parabola. One interesting thing to note here is I drew a graph, and it's a good one, but it's not the only possibility. I assume that I started with a big positive y value, but maybe I should have been starting with a negative y value. And in that case, what would happen is our slopes would get less and less negative, and then they would become 0 at this exact same x value, and then they would become positive and just get more and more positive. And this probably is not a perfect graph, but what you should see is the only difference between your two different possible antiderivatives here is vertical shift. It's just that plus c that you're seeing. So maybe this first one has a plus c, has a certain plus c, and the other one has a plus c that's 4 or 5 smaller than that. So there is some ambiguity when you draw an antiderivative. It's just one of the possibilities, and someone else's might be in a different spot, but the difference should only be vertical shift. Okay, asymptotes always make life interesting. So let's see, if we're going this way, again, we're going to take our slopes and we're going to make them our y's. So I would say, looking at this asymptotic behavior right here, our slopes are really close to 0, and they're very slightly positive, and then they start getting more positive. So over here, our y value should be really close to 0, slightly positive, start getting more positive. And then as I go, oops, erasing what I drew, it looks like they're just going to get more and more and more positive, and we get that skyrocketing. It looks like an exponential shape. So over here, we're going to go slightly positive, more and more and more positive, and then skyrocket. So notice the asymptotic behavior just carries through. You don't want to make assumptions about the formula for the graph you're looking at, but here it does make sense to think about if this were in fact exponential, what would we expect for its derivative? Excuse me. And the answer is something else exponential. So if this is a shifted exponential, because I see the asymptote is down, the shift would be like a -2, for example, and that will go away when you take the derivative. So that asymptote moving up to 0 makes sense because we lose the shift when we take the derivative. Okay, heading the other direction, we're going to take the y values and we're going to make them our slopes. So again, it can be helpful to identify when your y value is 0, that's a flat spot. Everything over here is negative, and everything over here is positive. We can say even a little more. As we head to the right, it's getting more and more positive. As we head to the left, it is getting more and more negative, but that's leveling out dramatically. So to the right, we're skyrocketing. To the left, we're leveling out and just about ending up with a constant negative y value. So that constant negative y value is really interesting because if you have a constant negative y value, that means you should have a constant negative slope on your graph. So let's just pretend that the y value of this was maybe -2. Over here, what you should see is some asymptotic behavior again. But this time, the y becomes your slope, so we should see asymptotic behavior where our slope is getting really close to being constant at -2. So here, m equals -2. So we have actually a slant asymptote that's showing up here. So we start really, really close, and then we're going to start drifting away from that because our slopes are still negative, but they're getting bigger as we go through right here. And then all of a sudden we're going to hit what was the x-intercept on our middle graph, and that's going to be the flat spot on this new graph. And then after that, we get positive slopes, and they just get bigger and bigger and bigger and go crazy. So no slant asymptote that way, just shooting up to positive infinity. Okay, so asymptote's interesting. If you have asymptotic behavior in your function, you should see that show up on the derivative and the antiderivative, but sometimes in interesting ways. So let's see. Down here, we've got more asymptotic behavior happening. So if we're taking the slope and making it our y value, what I would say is I could talk myself through this. My slopes are really close to 0, so really small positive over on the right, and then they get a little bit more positive, so here I'm getting more positive, and then they actually start getting less positive again, and right here my slope is 0. I was going to say back to 0, but technically it wasn't 0 to start off with, it was just really close to 0. So slopes are really close to 0. They get a little bit positive. Here. They get a little bit more positive, but then they start shrinking again and go back to 0. So something like this. This point right here, the inflection point on f prime, becomes this point right here, the maximum on f. And then to the right, our slopes become negative, and for a while they're getting more and more negative, but then eventually they start flattening back out again. So they're still negative, but they're now approaching 0. So something like that. And this is a horizontal asymptote still in the middle. if we want to take our, what do we want to do now? Our y's and make them our slopes for the antiderivative. You can summarize here. Interestingly, it's not a super exciting summary because they're all positive. But we can get a little bit more elaborate than that. We can say, okay, so my y values are all positive, which means my antiderivative will always be increasing. They're really close to 0 on the far left and the far right, which means my graph will be pretty darn flat. So we're going to start off pretty flat, and then our slopes are going to get more and more and more positive until I hit this peak on the graph of f prime. So this is, oh, what am I saying here? Yeah, I think I said that right. So our y values are very small positive. They get more and more positive until I get to the y-axis. And then my y values stay positive, but now they're getting smaller, which means my slopes stay positive, but now they're getting smaller. And as we head out to the right, they're getting really, really close to 0. And this is asymptotic, so actually now we have an asymptote showing up at the bottom and at the top. So that's a rough sketch. And again, these are rough sketch. So if your scale's a little different, that's okay. If you're shifted up or down on the antiderivative, that's also okay. Okay. Ooh, nice polynomial shape. Okay, so if we're taking the slope and making it the y, I would like to pick out everywhere where my slope is 0 to get me started. So 0, 0, and it looks like there's a flat spot in there. Let's see if I can kind of level that off over here. So the slope is 0 at that point, so the y value should be 0 on the graph of the derivative. Same thing here, slope is 0 on the graph of the function. The y value should be 0 on the derivative, and then somewhere out here, same thing again. In the middle, we can see that our slopes are positive but getting smaller in the middle. On the left, we can see that our slopes are positive and getting smaller. And then they switch to negative, and they get more negative, but then less negative. So my slopes are negative, they get a little more negative, they get a little less negative, and then they come right back to 0. After the second flat spot, we're back to positive. They get steeper for a little bit, they get closer to 0 for a little bit, and then fully flatten out. And then this last one is interesting because we don't actually have a shift. The slopes just go right back to being positive. Do not like this jaggedy looking shape. And I want to make myself a little more room. So they actually go right back to being positive and then just get more and more and more positive after that. Okay, so there's the derivative. So again, you want to read off your slopes from your graph and then rephrase that as not my slopes are positive and getting smaller, my y values are positive and getting smaller. When we do the antiderivative, our y value will tell us about our slope. So here it gets really interesting to look at when your y values are 0. So let's see if I can kind of block that off. I'll just put little tick marks. Say around here, and around here, and around here. Our y values were 0 on our derivative, which means we'll have flat spots on our graph. Okay, so we can say 0, 0, 0. We're looking again, remember we're looking at y's, so my y's are negative 0, positive 0, negative 0, positive. So over here, my slope should be negative, and again, you choose your starting point, and then 0 at that first tick mark, positive 0 at that second tick mark, negative 0 at that third tick mark, and then positive. And there's something slightly funny happening wherever this is. So here, these were our x's, and then somewhere in here is where the inflection point from f prime was. It's really hard to show what's going on there. What's happening is the graph is, we can go all the way over to second derivative. The graph is concave up because the second derivative is positive, and then it straightens out for just a second. There's no concavity, so concavity is positive, 0, and then back to positive. So positive concavity means concave up. 0 concavity means it behaves linearly at one single point. So this is bending up, and then it straightens out for just an instant, and then it bends again. So I would not be looking for that to really show up as anything, but just to point out that there is something going on there. It's just kind of hard to show. Okay, last one. Let's do a piecewise. Oh, I've got extra pages. Piecewise graph, and let's just say this is a closed circle. I can see that it's missing. Okay, so when we go this direction, we are looking at our slope, and we're making it our y. So I can see that I start with constant positive slope. So over here, I should have constant positive y value. I'll say it's about here. You kind of get to choose where that goes. Oops, let me be careful. Oh, did not mean to lose all of it. Okay, here at the end point, whether it's filled in or not, at the end point, it's a little ambiguous as to what's happening with slope, because we have a great slope on the right-hand side, but we don't have anything on the left-hand side. So generally those, we'll go through this in more detail in a little bit, but generally those endpoints are not going to, are going to have open circles. The derivative will be undefined. The same is actually true at the corner. We go from having a positive slope to a negative slope instantly. There's no smooth rounding out to let this just, the derivative graph just drop down. So what happens is that the pieces are completely disconnected. We switch to, ooh, and I think it looks like even steeper than the positive slope, so I'm going to move that down a little. And then that stays constant until we hit the y-axis. Once we get to the y-axis, it looks like we have another of these kind of jumps. All of a sudden, the slope jumps to being quite a bit steeper negative. So I'm going to start down here, but I would point out that some people, when they look at that, think it looks like they have a vertical tangent, which is possible. And if that were true, what you'd do is you'd say there's an asymptote there that's headed to negative infinity. Here, my slopes are negative, and then right in the middle, 0, and then positive. So for this one, my slopes are negative, 0, positive, right to about here, and there should be some symmetry because I definitely think this looks symmetric. So if you think that's a half circle, that's when you'd actually have the asymptotic behavior. If you think that's a parabola, then this could potentially look like a straight line on the derivative. I'm going with something somewhere in the middle, and that's completely fine for you to do as well because we are just estimating shapes here. And then the last piece is a constant function, so it should have constant slope of 0. Okay, so there's my derivative graph. For the antiderivative graph, I want the y's to tell me about my slopes. So here, I'm going to say, let's see, my y is 0. And then all through here, it's positive. And then, again, it's 0 at the y-axis. And then we stay negative for a bit. And then, oh, I drew over this too much. I can't tell, was that open or closed? Closed. Okay, so then it's 0 again right here. And then it makes a jump to positive. So it's not going to be quite that simple, but that'll get us started. So we want to actually start with a flat spot. So let's say way out here. We start with a flat spot. And then our graph is going to increase for a bit. And then it's going to keep increasing, but it's slowing down. So y values are getting bigger and bigger positive and then less positive. And then we need to hit another flat spot right at the y-axis. And then, let's see, our y value switch to negative kind of abruptly. And these pieces don't, well, actually I think they do have to connect because this wasn't undefined. So we'll say we're going to switch to negative. It's going to get a little more negative, and then it's going to get a little less negative, and then it's going to stop. And then we switch to constant positive 0. Okay, so to constant positive, head out something like that. So if you have a constant positive slope, that's going to be linear behavior. Okay, so again, this is pretty rough sketch, but there's kind of an idea of what the antiderivative function might look like. Okay, so there's lots of graph examples. Thanks for watching.